What's going on, everyone? Welcome back to another episode of the Deer Gear Podcast. Today, I am joined by the smartest man in archery, Dorge from Firenock, and one of his dealers, Dave Murray. These two discuss everything that you need to understand and know about arrow shafts. So it's kind of a fundamentals conversation, but it is crucial to understanding arrow flight. Is the way the arrows are made, why they're made that way, what you're looking for out of an arrow shaft, and what really matters. So it's a really good conversation. Again, we're going to be hearing a lot more from Dorge. So get your notepads ready and let's get into today's conversation. All right, guys, I'm back. I'm live, and I am sitting down as promised with Dorge, and we have a very special guest, Dave Murray. I want to thank you guys for joining me this lovely Tuesday morning.
Yes, definitely. Well, I'm so glad Dave will join us. Dave is one of my absolute top grade East Coast trainer for Firenock. I mean, a lot of you may not know, Firenock actually all the dealers, or what they call certified and trained dealers, I went through our training program. And Dave is one of my guys who train most of my dealers on the East Coast. And he actually owned Vital Limit, which is a very, very high-end custom shop who sell no bows, who only do upgrades of arrows. So his expertise is unquestioned, and his season of experience is also not questionable. Of course, sometimes we do question him. Well, today I want to talk about, I think as I promised, I will talk about, and I think that's one thing that everybody seems to know a lot, but not actually. So I would like to start today with what arrow shaft does and why is it so different, and why are we concerned with arrow shaft, and why it is the last product we find out actually put to our company as product, and why it takes us so long to come up with an arrow shaft, and why is it so misunderstood. I mean, the fact is that arrow shaft itself has been used since beginning of time when we humans start using with, bow and arrows. But that is such a big deal. The reason for that, because in the old days, cedar arrow and so on, what we are trying to find in the old days is trying to find a material that's as lightweight as possible, as strict as possible, and we're able to respond to the ability of what an arrow does, which nothing other projectile does, is that you absorb and translate and transmit the energy that was given to it, and then able to shoot it out correctly. Well, that's the reason in the old days we start with cedar. In the Western culture, that you start with cedar, and the Eastern culture they start with bamboo. But of course, as you guys can imagine, bamboo shaft have node, so that the entire curve is not perfect. And then we go into a split bamboo construction and so on, so we can get a pretty linear band shaft. Just remember that word, linear band. And then aluminum shaft come along, and then that's where we see the first time an aluminum shaft. It sort of solved all our problem of what an arrow should be. And to be fair with you, that is also the same reason why you see most of the Olympic archers, they still use aluminum or aluminum composite shaft. Now, I will go into aluminum composite and the difference and the benefit of each other. What we really try to do in this moment, as we understand the dynamics of an arrow shaft bend, is that, to be frank with you, that's before Firenock come along, my opinion is that there's no better shaft than an aluminum shaft. And people say, what? How can it be? Because 90% of the time, aluminum shaft have two ways to make it. One is called extrusion, which you put a part of metal inside a mold and you squeeze it out, you come out exactly the diameter. That's the first way and the cheapest way. And then the other one is called roll and seal, or what you call roll and weld. So you got a piece of aluminum, you roll them together to form into a tube, and you weld on one side, and you grind it on both ways. That's what a lot of people understand, and that was one of the normal way of making aluminum. Both of aluminum shaft will give you one distinct capability, is that they give you an arrow shaft that have an absolute linear. And I think that is one of the most critical and what everybody is looking for, but did not know what they're looking for. So that in the old days, when you look at aluminum shaft inside, you look at that, the seam, because of where the seam is, That's where an aluminum will bend as the high point. The opposite of that seam is where the arrow will bend. And this is where I think a lot of people were trying to sort of discuss or argue what a high and low spine is. Well, from my technical experience is that is no high spine. Yes, there is a high spine, but the only thing matter is the low spine. And the beauty of aluminum shaft is that you know where the spine is a mechanical spine because it's part of the construction. I think that is where things get exciting. And first for the people who do fishing, bow fishing, the fiberglass arrow come into play. But as you can imagine, fiberglass arrow have pretty much a similar characteristic of original carbon arrow, like the way the Beeman built it. Now, the problem with the Beeman construction, they're technically the same as the original first generation car. Again, it's extrusion process. So that you put this material, you go through this die, and then you squeeze out this piece, and then you went through a curing process. But all the fibers are linear, which is what a lot of people love, because then when you bend the shaft, as long as you're a pretty easy like fishing rod, you can pretty easily find the spine of the shaft. And as most people who do fishing rod, you can, a lot of people say it's high spine. No, you put the guy on a spinning rod on the low side. But then again, on the arrow shaft, the high side is not what you look for. It's the low side. And people say, no, we put the coffin on the high side. That's because you are thinking of the aluminum arrow again, not the carbon arrow, especially not today's carbon arrow. Actually, if you really think about it, carbon arrow should be split into three major categories. In the old days, there's two. The third one was introduced and patented by us. The first category is that you got all the carbon going from one side to the other side, it's extrusion. And that itself, right now, there is only one company left. I know that use similar approach. That's Derr Crossing. All the rest of the carbon company, except us, are using what they call multi-directional lathe. It can be 3, 5, 6, 7, depends on what you do, of layers. And each layer have a specific direction. Usually it's 15 degrees to the left, 15 degrees to the left, right, 15 degrees to the right again, and then 30 degrees to the left and 30 to the right, and then do a full 180 degree wrap over it. I don't want to go too technical, but in order to understand why carbon arrow behave like carbon arrow and the spine of a carbon arrow, this background has to be given. And then the first one, of course, the first company who used this approach, the multi-directional lathe, is Gold-Tip, in which you see the Gold-Tip arrow was one of the first few arrows that do a lot of great job. But when you do a multi-directional lathe, that was one problem. What is the resulting direction of the bend of the shaft? This is where everybody got confused. The answer to that question is that just think about it. If some of the fiber is pointing to the left, some of the fiber is pointing to the right, none of the fiber is straight. But then if the arrow bends, the bending is the resulting of all the fibers' ability to keep the arrow straight. So what happens is that arrow, when you flex it, it don't just bend up and down. You also torque from front to back, which in other words, that means when you launch the arrow, as the arrow bends, since the knot is anchored, the tip of the arrow can turn left or right while it bends. That's where the word torsion comes into play.
Now, Dorge.
Yes, sir.
You mentioned linear spine. What can you explain some of the benefit to that? Or there's like a consistency?
Yes, first of all, the spine is one of the most important words for any shaft. Because see, until you know how the arrow bends, you have no consistency out of it. Now, very simple. Let's take torsion, which is what we are going to talk about right now, out of the equation first. Just talk about bend. Imagine we have to think of an arrow from the middle point as a clock, okay? If the arrow bends point, the beginning bend point, it's a 12-foot clock. The secondary bend, that means we have to flex up. The arrow is now flexing at 12 o'clock point. That means the tip itself of the arrow is now supposedly pointing at 6 o'clock. And if the spine is flexing between 12 and 6 as the first direction, if you do not control it, just say on an arrow rest, and you are also not on the node, which we'll talk about the node maybe in a different discussion, because this is where the physical property of an arrow and arrow rest come into play. At that moment, the 12 o'clock to the 6 o'clock band, assuming that you test all your arrows on your arrow rest. Because remember, the entire launch cycle of your arrow, besides the nuts and the string travel, the only thing you can control, which is the most important, is your arrow rest. Now imagine your arrow flex between the 12 and 6 o'clock. That means the arrow launch now, you know the arrow going to flex and now push the arrow rest at the 6 o'clock point when it launches. Mm-hmm. That's assuming the arrow is a linear spine and the spine is flexing at 12 o'clock. Now, if you do not know that, and now you got another arrow that's flexed, the spine is actually, the soft side is actually now at 7 o'clock. That means it's going to put the pressure at the 7 o'clock point of your arrow rest. And what happened to 5 o'clock? It's not being pressed of your arrow rest. Remember, most arrow rests are two-pronged. So you got now, all of a sudden, your force is going to the side of your arrow rest, not on the dead center. And if your arrow, now, in other words, the launching point of your arrow rest is no longer the same for that arrow, then how do you expect the arrow to shoot the same? Right, you end up counting the arrow. But at the same time, if you ever use my pet PAP as the spine, the first dynamic band locator, what you're trying to do is that you want to put all the arrow, when you launch out of your bow, they all will launch at 12 o'clock and flex down at 6 o'clock. If they all come off the arrow rest, because think about it, your entire arrow, besides your knock point, is your arrow rest. That's the only two control point you have. Now, we all understand knock travel because that's how the push cycle of the deck. I mean, we're not talking about that because that's bow. We'll talk about that totally different in some mind, because that itself is more than a can of worms. It opens up a whole bag of tricks right there. Right, exactly. And that's the reason, the design of each bow they have that. I mean, it's talking about which of the high-end sport cut at 200 miles per hour is the best. I mean, there's no winner here. Everybody is, right. If you know what you're doing. So imagine this. So if you do not know how the spine is and you do not locate the spine of the shaft, now that's a misunderstanding. There is no high spine. There's only the first dynamic band. Okay? High spine was a word they used in aluminum arrows. And not to mention, now we understand that if we are able to find a way to the resulting of an arrow on the first dynamic band, I know that's a word that we'll keep on stressing. It is not the high and low spine. It's the first dynamic band. Because nearly all carbon arrow, besides the first Beeman arrow, until we come along, are all. That means the spine of the arrow shaft go from 12 o'clock, assuming that you find the very end. It will come from 12 o'clock, and then you turn yourself as inches increases. I said, wait a minute, it can't be, because at the end of the day, the arrow still flexes. I said, yes, that is the first dynamic band, which is a resulting band, not the physical band. That itself is not just the carbon fiber itself, it's also the final reaction of the point, the insert, the vein, and the knot. It gets very complicated very fast. And that's the reason most people say, oh, this arrow from the factory gives us a spine, and that's what we're going to use it. That sounds great if it's aluminum. Or in some way, it is actually like a Beeman with a linear spine. But in case of a multi-carbon lay, it's physically impossible to have a linear spine. Which direction layer fiber is the master? That is the reason you've got a resulting spine, because after combination of all the above, plus your vein, your knot, your insert, and your point, when they all combine, when you compress that, on the very node of the arrow, that's where compression point is, the arrow flex. That moment it flexes, which way it bends up, is your first dynamic band. That is where you make sure all your arrow bend this way.
Now, Dorge, you mentioned your PAP system, and there's a lot of guys out there that use the ram spine tester. That's something I used to use before I ran into you, and I realized I had to chuck that away to eBay. And can you explain some of the difficulties, perhaps, with a ram spine tester as compared to yours? One of the things that I've noticed was when I first got your PAP system, and I put the 12 arrows that I did with the ram spine tester on it to see how accurate I was doing them, I had maybe three out of 12 arrows that end up being correct. And those 3 arrows took me as long to locate on the ram spine tester as I would near the whole dozen arrows on your spine tester.
Well, actually,
or locator.
It is that what you're dealing with in the case of the ram is that is fundamentally, you need to understand why arrow bends and what caused it to bend and what is the material in it and why is it bend. The ram is fantastic for cedar arrow, aluminum arrow, because what it's looking for is the imperfection of the roundness of the Now, when you put an aluminum arrow, usually when you turn the arrow on the spine, you look at the dial indicator and say, this point of the arrow is higher and this point of the arrow is lower. And you're assuming that the moment the high point of the arrow shaft, the reverse of the low point is where they're going to flex. That is because of material. But in case of a carbon arrow, does the outside diameter of the shaft, the circumference of the shaft, have anything to do with how the carbon fiber inside is going to react? Think about it. In the case of beaming with a single extrusion when the fiber is pretty much on the outside, yeah, you can see that. But in the case of multi-layer, directional layer, you may be looking at the outermost layer of all 3, 4, or 5 layer carbon. So, and not to mention carbon, have one thing is after you extrude it, you went through the wrap process, you went through a baking process, you went through a die grind. So you push this shaft through a die and you grind the outside off. And remember, carbon fiber, if you look at it, you got a very tight wrap. That's called a skim. You wrap the whole thing to keep out the loop string of a carbon fiber within it. And so when you put that piece of arrow on a ram spine finder with a dial indicator, what are you really measuring? The finish of the grind. So
right.
What does the 3, 5, 7,000 difference from a circle to do with how the arrow? The answer.
That's another thing. Being you're bringing up numbers, a lot of these guys are going off of straightness. Like they have the mentality you have to buy a 001 shaft, and I mean, through the process of building arrows, found out that the straightness doesn't matter if you build according to the bend of the arrow. And I don't ever advertise straightness of an arrow because I know it's irrelevant. I've taken actually your first round of arrow weave shafts and vertical bow shafts and shot a sub 2.5 inch group at over 90 yards. And those arrows were like 8 to 13,000 straightness.
All
so
right.
at that point, what did straightness do for me? It was absolutely nothing.
Well, actually, the straightness have a certain amount of benefit, and people need to understand that the point of straightness is that because people don't understand the dynamic band, and they look for something, and that is something they have, and not to mention straightness of arrow is technically 100% marketing scheme. Because let me just, since I know the days I know the inventor of carbon arrow, which is the first CEO of Gold Tip arrows. You need to understand your Gold Tip Pro Hunter, your Gold Tip Hunter, your Gold Tip XTs. They are 100% identical arrows. Yes, they're 100% identical arrows. The only difference is that they put them on a testing machine. In the arrow industry, to test the straightness of arrow, this is what is tested. You got a rolling table of 28 inch apart. Then you put a laser beam down in the middle of that. You rotate the entire shaft one full turn. And your laser have less than 1,000 variants. That is considered a 1,000 straightness arrow. Just think through what I said. What happens if you got an arrow that is bent on that 3 point in the S form? It can be 15, 20,000. But for that test, it is a 1,000 straightness arrow.
When you go to shoot the arrows, I mean, I've done some high-speed video. There's a lot of high-speed video out there. These arrows flex sometimes pretty significantly, especially when you get into longer arrows, like irrelevant.
Well, first of all, we need to go back and ask ourselves this question. This is, I think, one of the most important questions that people need to ask when they want to understand arrows. I mean, arrow flex. When is an arrow ever? After you shot it. When it was straight and not move when it hit the target and stopped. The fact is that most arrows, after the initial launch cycle, go into the Archery Paradox and the flexing. It's about about 50 to 100,000 flex in it.
And then it's subject to torsion on top of that, because that
would screw your brain so much. I mean, just like when I talked to a field professor about the belief principle of aerodynamics and torque, they all can handle it. The moment we add torsion in a combined helix, it's like, holy cow. Some aero just, you prefer, they are not arrows. They are called tomato sticks because of that.
I mean, learning a little bit about torsion, you know, and then hearing some of these guys, when they shoot deer, the arrow breaks in the back, you know, it makes me think that, you know, the point comes to a sudden jolt hitting the animal or target, and then you got the back of the arrow that still wants to turn, and you got to think it's like a pool noodle and just snap it off at the back.
Well, actually, the entire process of torsion and flex is actually more important. I really want to sort of delay that until we go into broadhead flights, and also after we finish, I need to understand in the fundamental of how the arrow flex first. Now, I mean, I want to go back to the RAM and the first dynamic band. As we say about using the RAM is fantastic if you are looking for the spine of a linear shaft, and the perfect imperfection of the shaft is where the band goes. That too is the fundamental principle of a RAM. The moment we go into a carbon arrow with a multi-layer carbon arrow, first of all, the linear spine doesn't exist anymore, which makes the RAM less valuable. The second is that we also have the torsion of the shaft with the helix spine, and the imperfection of the shaft have nothing to do with the band. The moment you understand these three, the RAM becomes useless. Now, to make it even more useless is that the moment you got a shaft, see, the RAM is based on a 28-inch band. Now, we already know that in the new carbon, in the northern day carbon arrow, it's a multi-layered. That means the resulting band of the shaft dictated by the length of the shaft to start with. So if you use a 28-inch only RAM finder, you got a 27.5-inch arrow. How are you going to find it? It is not linear. So every single length of the arrow is different. So just like when I first designed mine, I end up with something like 80 holes on my RAM finder, because every single arrow I put on it, there's different length. I need to adjust that rollers so that it will match the length of the arrow. But at the same time, you know, you can't just put the arrow, you can't put a RAM ball bearing on the end of the arrow, because now you're dealing with tangent. Because when you put the arrow on the normal bearing, a ball bearing, the edge of the ball bearing, you're measuring on the edge of the ball bearing. That means your force on that bearing for measurement is now being pushed from the side of the ball bearing to it. And then if you look at the Ram's design, is that you got 4 ball bearing with a hook in the middle. No, actually 2 hooks like this.
Let me ask you a question. If you take a 32-inch arrow and locate the first dynamic bend, and let's say we cut the arrow to 28 inches, most of the arrows out there, they're going to be the same, or is the bend going to change?
Totally based on construction of the shaft, it is an unknown. I mean, the one thing that you can find out, I mean, if you want to use the strength, use any arrow, is that you can use, the best approach is to know how true this is. You find a 26-inch separation, you push the arrow down, and then you mark it. You will turn a little bit and you mark it. Then you push the arrow from front to back. You find out that point keep changing. That is the proof of the first dynamic band being linear.
Because in the past, I've built on several different shafts. One of them's Victory. Victory has a nice shaft. And, you get the shaft, they have their little pre-spine located marks.
Exactly.
Well, not everybody. There's a guy that's 5'7" who shoots a 26-inch draw length. He's not shooting a 32-inch arrow. So when I cut the arrow and then I put it back on the paps just to double check the spine, there could be like 15 plus degrees different where it was located, and I got to remark it. So that little indicator, at best, and I found these that could be a little off as well. That indicator is only relevant at that length of shaft without having the need to actually double check it if you make a cut. And I've tried this, even just cutting an inch or two off, and notice that it'll shift as I cut.
That's exactly what a helix spine do. Because a helix spine will give you a final resulting bend. And that is the length. That's the reason the length of the shaft and how long the shaft is. And that's the reason I said, when I own the ram before I make the PAPs, is that I got so many holes on it because I need to keep on putting the ball bearing support into a specific length. Because even if you build some guy with a 27.5 inch and somebody with a 28 inch, the support need to be different. Because you need to optimize the total length of the shaft. And if you're a really specific target shooter, the length of the shaft is more critical than most because that changed the reaction of the shaft to your bow. But that itself is even minor compared to where the node of the shaft is. We'll talk about that when we talk about aero concepts, because that itself, as I said, that's where the knowledge of aero shaft and how it bends become critical. But we today, I think I really want to bank in the basic concepts. A carbon aero shaft is helix in spine. And in most cases, now, this is getting even more interesting. What we're talking about first dynamic bend, people say, interesting. Well, then we want to go into the understanding the multi-layer and the helix spine. We now know. Now we have the first quote-unquote dynamic. The problem with the first dynamic bend is that then where's the second? I think this is where a lot of people got confused and got totally, we got Dave back.
I don't know what happened there.
That's okay. The second dynamic bend of a helix spine is where things got even more interesting. Now, in the old linear carbon, the first dynamic bend, say, assume it's 12 o'clock. The second dynamic bend is at 6 o'clock. What does that mean? That means you now got a neutral plane the aero flexes against, isn't it? There is aero flex between 12 and 6. But in case of multi-layer carbon, this gets really seriously sort of screwed up and complicated. The first dynamic bend, assume, is at 12 o'clock. If the aero is well built as a carbon aero, the second dynamic bend is around 7 o'clock or 5 o'clock. Think about it for a second. It is an arc, not a what you call it, a diameter, isn't it?
Right. And
it is twisted very badly. That's where things get so screwed up.
So you can have one or two of these bending points, and really sometimes once in a while I get a third in there.
No. You don't understand. On extruded aero, you can have up to 7.
I've heard about that. I haven't experienced that many, but 3. I get a couple shafts once in a while on other shafts. I haven't really experienced them on your shafts.
But in most cases, when you deal with a shaft, the 2 weakest point is where the aero going to flex against. The third one is insignificant. But the third one is need to know, because this is where things get screwed up real fast.
That some of these guys out there that are thinking stiffness of the spine and are trying to measure these things don't realize that you got you got the load point of the bow. Mm-hmm. You got to not compress it against the point weight, and it's going to naturally want to flex.
Oh, you're going to flex
basically
a lot more.
What we're trying to do is predict that in a direction to get consistency off of that.
Well, and that is where the problem with today's aero building is that we compress the bow so much more, and the spine becomes so important. And in the old days of the recurve bow, it's not that bad. And that's the reason, if you talk to a recurve guy, they will tell you, this is so important. You must find the spine of the shaft and so on, so that you were pointing above the 12 o'clock of the bow when they turn it. So they have the spine somewhere around 35 degrees to the left, if they are a left-hand shooter, if you're a right-hand shooter.
Now, on a traditional sense, I mean, I don't do a lot of traditional stuff, but a traditional shooter, you got to almost locate the spine and then fletch it accordingly based on its shooting style.
Yes, exactly. Again, because see, the traditional shooter, they're shooting off the shelf. The flex of the arrow is actually off the shelf of the traditional bow shelf. There is no arrow rest. But in case of compound bow, especially modern day compound bow, we have a super precision arrow rest.
And in regards to crossbow, because we got rail systems, we got what's called, I guess, semi-railless. There's no rail systems, but in regards to railed crossbows, use Scorpid as an example. We want the spine so that the arrow, the spine location, so that it flexes up away from the shaft versus have any chance of pressing down into it and causing any kind of chatter. Now, with your cameras, I've filmed this in high speed and broke it down furthermore on software that we actually went during launch cycle. We actually captured this with the arrow flexing and slightly coming off of the rail during launch cycle, which is exactly what you would say you want to happen.
Well, absolutely. But see, what we do, we go too deep, too fast, and too wide. I think what I want to take out today is that, first of all, we need to understand there's multi layers to a carbon shaft today. And then the spine of the shaft is here. So understand that 2 points. What you need to do is, I want to add this part to it, because this is what I really want to bring in today, is that the fact is that the shaft is helix and the first dynamic band is bending. And we want to stress one point. As you find it, you build it. Does it mean the arrow is good forever? Because see, I did not say that in the case of aluminum arrow, they're only good for 70-something. Do you know why? Just like when I was at my discussion with the Olympic gold medalist Rod White. He's a very good friend of mine. And I say, Rod, then aluminum arrow is the best. Why would you change? Because on the class of aluminum arrow and you shoot the right spine, there's metal fatigue. The moment you shoot 70-something shots out of a good aluminum arrow that's correctly spined, you shot the spine. That means if you shoot with a 500 spine shaft, like the Olympic guys did, that shaft became, after 70-something shots, this 500 spine can become 600 and beyond. The reason that we like carbon arrow, because carbon have such good recovery. You can literally, if you build correctly, a carbon shaft spine, the spine rating of the shaft will not change, even under hundreds, if not thousands of shots. Now, let me go back and say one thing. The definition of a spine rating is that you support an arrow at 28 inch apart, and then you put 1.93 pounds underneath it, and the arrow now flex down. How many thousands it flex down is the spine rating of the shaft. That means if you say, I got a gold tip 246 or XT, that is 400 spine. It means that if you put 27 inch apart, you drop the weight of 1.93 pound, 1.92 pound on it, it will drop 4 thousandths of an inch. That's your rating of your shaft. The larger the number, the weaker the shaft. That's the reason a 300 spine is stiffer than a 350, is stiffer than a 400, because a 3,000 drop is 10,000 less than a 4,000 drop in the weight after you put the weight on it.
Now, Dorge, you mentioned layers of shaft. I think you mentioned earlier that some of these shafts out there have maybe like 7 or 8 layers.
Yeah, it depends on the construction and the approach. In most cases,
how many layers does your shaft have, your arrow weave?
I don't want to go into that for this moment yet, because it get into, it's all ridiculous. Because that's an engineering approach than others. But I want to go into how the concept of a shaft, the concept of helix spine. Now we'll talk about a little bit more about how, okay, we know that all carbon arrow is multi-layers, besides beaming, it may be a deer crossing, and then we know the spine, how they react. And now we understand torsion. So what do we really want? What we really want is a shaft that flex without torsion. Am I right? An unworkable animal. Because nobody understands it, but it actually exists. As a matter of fact, if you look at 90% of the video out there on the target shaft, You notice when you shot it, the guy say, "Oh my God, look at the vein turn left, and the vein turn right, and the vein turn left." If you take a closer look at the point, I mean, imagine if the arrow shaft have torsion on it. After you first shot it, the arrow is flexing, right? Assuming the arrow is talking to the left to start with. I mean, right hand talking to the left, then it's turning from right side on. The point of the arrow now is doing a clock, right?
Right.
After you launch it, the arrow is coming back again. The knot is now off the string. What does Newton's second law say? Whatever is moving forward, you keep on moving forward, right? So at that very moment, what's going to happen to the vein side and the knot side? It's lighter. The heavier weight because initially on the first bend, the point of the knot is turning to the left, from right to left, doing clockwise. The moment the shaft is off, that dictates, and the second bend, the shaft had to flex, is reacting the opposite direction. Because remember, the flag itself a torsion. The first flag is the front is turning left. The second flag is front is above. The shaft is already left. The point is turning already. Your vein turn back to the opposite direction now. That's what torsion do. And that's what every carbon arrow does. See where the problem is?
Right.
If during this whole launch cycle, the arrow shaft and vein go backward, forward, because of torsion. So the higher the torsion, the worse it gets. Because what happens when the vein is going backward, forward, left and right, What do you think the aerodynamics is going to be? Oh, screwed up, isn't it?
Right.
It's like a total chaos. And that's the reason people will tell you, shoot the heaviest spine you can, because the heavier you get, the less effect all this has.
Into a conversation about concept system.
Yes. I mean, that's all because of understanding. So we need to understand all this concept first. So knowing that with torsion is detrimental, all this is not important until we reach about 2015. Because every bow we know of moved from your basic 55, 65, 75, 85, 90%. The compression of the shaft becomes significant. That's where everything showed up. It showed up badly, really badly. And that's also the reason that people start using heavier shaft, heavier weight. You know why?
To try, well, a lot of shooters I get, they'll say, I want to jump up a spine just to reduce the bend, make it stiffer, better. I mean, that's the idea, project it without the other compensation.
They do three, that's what they did. They actually do three things. They make the bow slower. So everything, that problem you have is no longer exaggerated like you're seeing. Second, they make the entire cycle of relevance less because the arrow is stiffer. So all this stuff become less relevant.
Right.
Let's step back a little bit and then talk about what the problem is. The problem, remember we talked about how strict the arrow is, first bend and so on?
Right.
There is also one factor in it that most people do not understand, is that carbon arrow have memory, just like aluminum arrow. But the arrow is not from carbon. The memory is from resin. So in other words, after you build the arrow, in the case of carbon arrow, you shot it for 50 shots. Do you know the spine can move?
Right. Yes.
No, it didn't break down, it shift. Because see, the carbon of multi-layer with the resin, the carbon fiber, because of the flex, some of the resin break down, not the carbon fiber. It shift. That's the reason some carbon arrows, depends on how well you build and what the grade of resin and the compression, and also the baking processes.
Here's a question. Can the carbon arrow shift on, but does that mean the exterior grind is going off of, say, by using a ram spacer? Does that ideally stay the same? Because now we got a person that
don't. That's where they call the memory effect. As a matter of fact, this is first recognized in the case of fishing rods. And that's also reason that a lot of people use, just like if you lay a bunch of fishing rod against the wall in a corner, as times go by, you pick the fishing rod was lean and bend based on how it was lean, which is also the reason that told people, when you store your carbon arrow, make sure you store them in an arrow box, not just lean against the wall. because it will cause the thing to lean. And then you've got memory effect. But at the same time, memory effect can kick in and start shooting it, just like the aluminum arrow. But this time it's not because of material fatigue. No, I'll take it back. It is because of material fatigue of the resin, not of the carbon. Because remember, carbon fibers are independent. The resin is what bonded them together. Yes, the carbon fiber will not get tired, but the resin does.
You got some shafts out there that have this metal mesh in them. What do you make of that?
That's an interesting approach. That approach actually is not bad as long as you have maintained an absolutely consistent temperature.
Well, using that kind of a shaft with just say some sort of metal mesh or twining in there, as metal flexes, how is that maintained in the shaft? Because usually metal and carbon really don't go together all that well when it's incorporated like that. And then does the metal fatigue at some point, like aluminum arrow being?
No, actually it does not. The problem is that the metal, and first of all, you need to think about metal and carbon. Metal, first of all, don't bond with carbon. Cannot. The only thing that metal was inside a carbon shaft worked is that metal would bond with the resin. The problem with metal is that as long as you maintain your temperature consistent, that's not a problem. Now we need to look at the expansion rate and the contraction of a metal based on temperature. That's the reason I stress that's a great idea as long as you shoot in a consistent temperature. But then if you hunt in cold weathers, what do you think is going to happen between the resin and the carbon? First of all, resin got harder as temperature drops. And when you deal with metal, the expansion and contraction in super thin ones, especially you also are dealing with the fact is that the carbon and the resin is only glue that put everything together. I personally think that as long as shoot it in the, say, control temperature, that itself has some benefit to it because it itself now have given the shaft mechanical control. I think that's an approach to what the linear shaft is supposed to do. I really do.
And there's some shafts out there they got a whole aluminum tube inside of a.
Oh, that's actually a great approach. I mean, if anybody who shoot the old ACCs will tell you, those are the best shafts. The fact is that we human at this moment can make the best shaft with strictest shaft is aluminum. There's no doubt about it. But because of the memory effect, because of the metal fatigue, one of the best approaches is put carbon on top of it. Then people say, wait a minute. Wouldn't it be better if we put carbon on the inside? Well, this is my personal opinion. That's the absolute worst. Because the dominant should be the carbon. The retaining should be the aluminum. My personal opinion is that if I was choosing a shaft in my life to shoot the rest of my life, besides my current shaft that I made, the best is the AC Super Slim made by Easton. There is no better shaft. And at one point, ACC Pro Hunter is the rebuild of the ACC 349 with different layers. The reason aluminum is so good because we know aluminum is straight. Aluminum spine is linear. By using that as your base, you put carbon on it. The carbon is going to now giving a mass memory effect to the aluminum shaft and give it longevity. So that approach, I really truly believe whoever thought of it is a very, very smart man and truly understand Aero. And that also resolves a lot of problems because see, when you got aluminum in the base, when the arrow flexes, the aluminum is going to dictate how that's going to flex because it will give you that. Unless there's so much carbon. That's the reason the ACC Pro Hunter, the moment you pass the 300 spine and up, it's not as good because the carbon take over now. So what all the bad thing about carbon is, so the ACC 349, the ACC 300, they are still okay. The moment you go to ACC on the larger one, they're not okay. Because now you got a dominant, whatever is dominant. Because back in the AC 349, the aluminum is still the dominant. So the spine is still linear. The carbon is doing the protection of the memory effect of the memory fatigue effect of the aluminum. I mean,
okay.
This arrow shaft construction discussion can be real deep, as you can see. I mean, every time we touch a subject, I got a full history to back it. But then I don't want our listener to get so confused. And we technically talk for an hour, and I'm not sure they want to listen to all this rumble jumble. But what I really try to bring back is that we need to understand why an arrow shaft flex, which way the arrow shaft flex, what are we trying to do? Before we sort of get off today, I want to talk about what do we really want an arrow shaft then? Arrow shaft with a really, really good spine, which we know we cannot get to on today's carbon shaft because it's multi-layer. In other words, we're looking for an arrow shaft, hopefully with the same characteristic of aluminum arrow. We want an absolute linear spine that do not change. The second, we want the arrow shaft to be as well constructed as the carbon arrow with multi-layer so that it would be durable and repeatable and consistent. We also do not want the fact we do not want the fact the arrow, we don't want the arrow to have torsion. And we want to flex one direction so that when if anything turns, it's because of the vein. Now, I mean, another day I will tell you, do you know by serving the direction of a string can turn the way which way the arrow turns? And it's proven. First of all, it's not a joke. It is proven. So when people say, oh, my arrow naturally turn left or right, what they're talking about is torsion. So imagine if you got an arrow that is linear spine, and you know the way you know your serving of your string, you absolutely control over all the elements, isn't it?
Right.
Before I close today, I would just tell you, we at Firenock achieved that. As a matter of fact, we proved that with 2 U.S. patents issued. We are the only company who make an arrow shaft that is linear spined and with no torsion. If anybody interested in this, I didn't want to go into this, but think about with every single thing we talk about, it's all the bad things that we do not want. We actually engineer one. So if multi-directional lay is the problem, why not we directional lay it? The answer is that if we do that, you have no loop string, the arrow explode because when you flex it. So of course, the best way to approach it is to use multi-layer cloth and control every direction of the carbon fiber.
And that's what you use.
Correct. But then I didn't want to go to too detailed because you're going to full engineering blow up. We can have a 3-hour discussion on multi-lay, but we are not going to do it because that would sound like an advertising deal. I want to think about it. If you know all those, what we talk about as bad things, and if we can overlay and eliminate all of the above, you're going to arrow that's perfect, isn't it?
Right.
But just like everything perfect has one downside, because otherwise everybody will build it. Let me just give you a hint. If I go to today in Vietnam or China and ask for Aero Pro Hunter, on material cost, you're looking at about 45 to 55 cents. For me to build Aero Weave 166, the material cost is $6.
Wow.
Just think about that for a second.
And you don't do no third parties like
nope,
a distributorship in order to keep that down a little bit.
Because in US, it doesn't matter if you cost 45 cents to make an arrow or cost $10 to make an arrow. The US government on the excise tax will take 53 cents per shaft.
And any other manufacturer that will put it out there in the market for everybody to have at it, how much would that set of arrows cost?
Usually, you figure the material cost, the final production cost, be 10 to 15% of the arrow cost, final price.
Well, what I'm saying is, as a retailer, as a consumer, if you want to go buy your arrows off of, say Lancaster had them, if we were in that predicament where, say, you were like a Gold Tip or a Black Eagle, how much would your arrow weave shafts cost in that perspective?
About $1,500 a dozen.
Yeah, and they're selling for retail what, one?
No. It's 200 something.
Or two.
Just bare shaft.
Okay.
Because this is where the problem that those people don't understand. In the arrow retail market, that's a different. We will close it today with that. If it costs you 50 cents to material, that should cost you another 50 to 70 cents for the manufacturing process. Now the arrow is about $1.20. Then you got shipping. Then add another 40 cents to it, $1.60. Okay, you got it at $1.60. Then you got an excise tax of 53 cents. So now you book at $2.10. Make it a dozen. You're already at $24. The first distributor won 40 points. Well, then you're looking at about $50. And then you remember that's advertising and everything. And then your retail guy in today's world won 40 to 50 points. Well, that 45 cent manufacturing cost, you just become about $100 in your hand. And I just want people to understand the few things. Just how much it costs and how much you found it, give it to him. Because the more hands you go through, the more expensive it gets real fast. Because if everybody wants, say, 10 points, it doesn't have to go through 3 hands. It's already more than you want. I mean, just like when those days I learned about the Japanese retail channel, now you know why. When the big guys come in and take the middle guys out, that is a lot of money to be made. Well, I think that pretty much concludes what I want to talk about the what the history of the Aero and also the spine is. Yeah, because I really think that you need to know fundamental what the shaft do, what you try to accomplish, and why are you seeing the problem. Until we fully understand that, we can't talk about building. Yeah, I mean, just like, can you imagine today, everybody talk about the original, original truck was built on a wood frame. Can you imagine in today's truck on a wood frame, not even on a steel frame. You need a steel hydro frame, just like sorry, I go in the wrong subject. But until you understand the material and the approach to build it, you don't know what you can do with it. And that's the reason I want to dedicate our first with this podcast on the fundamental of aeroshaft. The more you know, the more you find out how much you don't know. That is the best phrase I've ever heard. And that is so true when I go into archery. I figured that being academic, educated scientist, nuclear physicist, went through project management, being a BMP, went through engineering schools, doing all the projects. This stuff is easy, right?
Right.
Oh, yeah, we'll talk about that in the subject about veins. That's going to be a discussion of myself. All right, Cameron, I think we should just call it for the day and then let our listener come in and maybe with questions or comments and so on. If they like it, I mean, we know this is for them. And the whole process for this is to educate. Let me tell you something that I learned when I was doing the ASA. In the hunter class, which is your average, a little bit above average show guys, he will go to the ASA shoots with a dozen arrow. There's about 2 or 3 arrows in the first hole of this quiver. Remember that 3 holes on the side quiver? That's all the arrow he's going to shoot right. If he lost that 2 or 3 arrow, he's done. What Dave is saying that with the correct field of just like expert like him, all 12 arrows is going to shoot the same. And we're going to tell you how on the next few podcasts.
That's perfect.
Awesome.
I think that's a good place to wrap it up. I want to give Dave a chance to, if anyone has any questions for you, Dave, where can they find you?
I have a website, vitallimits.com. I have a phone number on the website and I have an email right on the homepage. Dorge has sent me over some of his cameras that I do some high-speed video work with. I've got some of those videos posted, I believe, right on the page. It'll bounce you over to YouTube also, where you can see some more of them. I would tell people, not only if they have questions, they can bounce, some of them over to me, but, check out some of these high-speed videos. I mean, we have them that, you can literally watch the arrow rotate on impact and see water droplets coming out of the water bottles that we use for testing. There's one of the videos over there that shows dynamic bend working off of the shaft or working off of the crossbow within launch. We can show rotation happen. I mean, there's a bunch of things that are going on in there that you can learn, just off of one video. So I would encourage, looking at some of them videos, email me or call me up with some questions on that. But vitallimits.com, they can find and source everything right from there.
Perfect. All right, guys. Thank you.
Thank you so much, Cameron, for the help.